Hey, welcome back to Fat Mama Physics! In this video, we're going to talk about scientific notation. So I'm going to go over what is a scientific notation, why we use it, how to convert a number to scientific notation and back, and as well as manipulating numbers that are in scientific notation form. So to get through all that, we gotta start now, so let's do it. Scientific notation, why do we use it in science? It is a shorthand. You don't want to keep writing a bunch of zeros. It's too much. The other reason why is later on we're going to learn something called a significant figure. What are significant figures? Numbers that are in scientific notation convey significant figures very clearly. So that's the other reason why we use it. So what is scientific notation? Generally, you'll see this format. So you have a number. So it looks like this. You have a number that has a decimal right afterwards, some other trailing numbers, whatever that is, times 10, and usually there's an exponent that is attached to the 10. I'm going to use for whatever purpose. It doesn't matter, okay? So notice it's a condensed form of a number. If I wanted to expand this number out, how would I do that? Well, we first look at, we're multiplying 10 to the power of 4. What that means is it's multiplying by 10 times 10 times 10 times 10. This is essentially 4 zeros. So that means I need to take that decimal and I need to move it forward 4 steps. And if this is a positive exponent by the 10, it means this number is greater than 1. It's going to be a big number. Big number means you got to move the decimal, well, it's the other way for you. Move the decimal to the right, making the number bigger. So this is 4 steps, 1, 2, 3, 4, okay? So that's where my new decimal is going to be. If I had to write this number out over here, this is going to be 6, 7, 9. And notice how I went over 1, 2 more spaces. And I'm going to fill those 2 spaces out with zeros. So there's going to be 2 zeros. And that's where my imaginary decimal would be right there. Okay, so that is a scientific notation. If I had to write this number out, it would have these 2 zeros. Imagine this exponent was much larger, like 13, 20, 100. Good luck writing those zeros, okay? So, here you go. Here's a positive exponent, numbers greater than 1. We gotta move the decimal point to the right to write this number in scientific notation, okay? Now, if, on the other hand, if the exponent was negative, is probably what you're asking, so that would look like this, 6.79 times 10 to the power of negative 4. What that means is instead of having 10 times 10 times 10, that's essentially 1 over 10 times 1 over 10 times 1 over 10 times 1 over 10. Or that's 0.1, same thing as it being 0.1 times 0.1 times 0.1, etc. Okay. So that's moving the decimal backwards, making the number smaller over by 4 decimal places. So I need to move this decimal in a way to make my number smaller, and that's moving it to the left. So that's 1, 2, 3, 4. So if my decimal place is there, I need to fill these empty gaps with zeros, and that is my new number. Writing it out, I get 0.000679, okay? So that is a negative exponent moving the decimal point to the left to get your actual number, okay? So this allows us to do question 2. I'm sorry, I'm jumping ahead, but I just want to keep the flow of the lesson here. So doing example 2 first, we can do A, B, and C now because we know how to convert scientific notation to regular notation. Let's try that right now. I'll do A, and I want you to try, actually, you know what? I'm going to do B, okay? I'm going to do B, and you're going to do A and C, all right? So B here, I have 7.1 times 10 to the power of 6, meaning I'm going to move this decimal here 6 places, making my number bigger because it's a positive exponent. So 1, 2, 3, 4, 5, 6. Over here, I have 1, I'll write it down, 7.1. So that's 7, 1, 1, 2, 3, 4, 5 zeros. 1, 2. There you go. Okay, so that's regular notation for 7.1 times 10 to the power of 6. Okay, so now it's a good time to pause the video. You're going to do question 2, A and C. Okay? Good luck. Okay, I'm going to do this very quickly with you. So, A is 5.5 times 10 to the negative 4. Moving a decimal place to the left 4 times, I get 1, 2, 3, 4, and 55. So 1, 2, 3, 4. There you go. Okay. So that's number 2A. 2C. Okay, I have 1 times 10 to the power 3. That's 3 times, moving decimal place 3 times. So 1, 2, 3. There you go. Okay. Alrighty. So now we know how to do that. Okay. It's time to go back to example 1 now because we haven't done that. Okay. And in example 1, it's we're going to do the opposite. So how to take a regular notation, regular number, convert it into scientific notation. Okay, so basically it's everything we just did, but backwards in a way. Another way you can think about it, well, let's just do A and C and I'll show you what I mean. Okay, so now we have a big number with a bunch of zeros, converting it to scientific notation. Imagine you have an imaginary decimal where it should be, and what we're going to do is count how many times this decimal moves to tell us how many powers of 10 we have. And when do we stop? We always stop before reaching the number that is a non-zero number. So right there is where I want that decimal to be. Not to the left of the 5, not 55. That's not proper scientific notation. Okay, so please be mindful, and this is where I see a lot of problems, is putting the decimal in the wrong place at the end. Okay, so it always goes after the first non-zero number. Always. Otherwise, it's not proper scientific notation. Okay, so let's count. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so that's 9 steps. So I get 5.5 times 10 to the power of 9. 9. Some of you know German. Okay, so I don't need to care about all these trailing zeros or anything else, unless this was 5, 5, and then 1, then I have to put a 1 there, but that's not the case. Okay, so that's my answer. So I'm going to do C, B, and D are yours. Okay, now C, we already have the decimal in the number, and again, we always want to move this decimal in a way that it is going to fall after the first non-zero number. So that's going to be right there, right after the 9, which is a non-zero number. So I count how many steps? 1, 2 steps. So I get 9.1 times 10 to the power. Now notice this is a number smaller than 1, meaning I'm going to have a negative exponent. So I know I need to put a negative sign there. How many times did I move my decimal place? Twice. So I get negative 2 at the top. All right, so you do B and D. Good time to pause the video. Okay, let me do B and D very quickly. So that's 780 decimal here, twice, 1, 2. I get 7.8, that didn't show up, 1, 2, times 10 to the power of 2 for 2 decimal places. Positive because it's a number greater than 1. Next, when I have this number here, it's there's already a decimal there. I move it until it's after the first non-zero number, 1, 2, 3, 4, 5, 6. Okay, so that's 3.004 times 10 to the power of, not positive, negative 6. Okay, those are their numbers. Hey, now we know how to flip back and forth. Let's see if we can manipulate some scientific notation numbers. Okay, so this is going to hopefully recall some memory of how to do your exponent laws. So I will circle the ones that I will do and leave the blanks for the ones for you to do. Okay? I will do A, I will do B, I will do E, and H. Okay? So let me do A first. Okay. I have 10 to the power of 3 times 10 to the power of 5. What that really is I have 3 10s that are multiplying each other, and then I'm going to multiply 5 more 10s. So 1, 2, 3, 4, 5, okay? If I count all the 10s up, I'm pretty sure you know how to count. That's going to be 8. 10 to the power of 8. Now, you might be thinking, oh, Miss Lee, you don't remember your exponent laws? Oh, yes. Now, if you're a little bit clever about that one, you remember that one of your exponent laws is whenever you multiply numbers with the same base, you add up the exponents. So 3 plus 5 is 8, just like how you have 8 10s that are multiplying each other. Okay? Straightforward, hopefully. Next one, we have B. 4 times 10 to the power of negative 3 times 5 times 10 to the power of negative 5. If you want to imagine there are some brackets to help you visualize the scientific notation part, by all means. And there's another thing you should know about multiplication is the fact that when you're multiplying numbers, it doesn't matter the order which you multiply them. So I can choose to multiply 2 numbers as I wish. The ones that are going to make my life easier are if I multiply 4 and 5. What's 4 times 5? 20, you say. Yes. Okay. And next, what up? We got 10 to the negative 3 and 10 to the negative 5. We just learned that if you're multiplying 2 numbers that have the same base, we add up their exponents. Negative 3 plus negative 5 is negative 8. So that's 10 to the power of negative 8. Are we done? You think we're done, don't you? I knew I would catch you on that one. If you didn't get caught, good for you. So a lot of students make this mistake of leaving the answer as such. We need to make sure that our scientific notated number has to have only 1 digit, then a decimal, and that this one, 20, violates that. There are 2 digits after an invisible decimal. That's a no-no. We cannot do that. So how do we fix it? Okay. Good way to fix it is, imagine you have 20, so that's essentially 2 times 10, yeah? If I have 2 times 10 and times 10 to the power of negative 8, then I need to just bunch up these 10s together. What's 10 to the power, what's just 10? What's an imaginary exponent for 10 to whatever, 10 by itself? If you're thinking 1, you're correct. So there's an imaginary 1 up here. I can just have 10 to the power of 1, and that's just 10, right? So if I have 10 to the power of 1 times 10 to the negative 8, 1 plus negative 8, that's negative 7. So that's 2 times 10 to the power of negative 7. You might be thinking, oh, Ms. Lee, couldn't you just move the decimal place over 1 and then just make that a plus 1 that gives us minus 7? Sure, of course. You have your shortcuts. I will explain things longer than there are shortcuts. But if I explain the shortcuts, then I will lose some people. Okay, so that is A and B. How about this? I give us a break. You do C and D, yeah? Okay, good time to pause the video. All right, I'm going to do C, just like you did by yourself. So again, this is the same base, but now we just got different exponents. Different, hey? Not really. So negative 3 plus 5, that's going to give us positive 2. So that's 10 to the positive 2. Okay, pretty fast there. Now we got this again. We got 2 scientific notation, notated numbers multiplied by each other. I'm going to do the same thing I did in B, which is I multiply these numbers first. So that's 8 times 1.2. So if I do some multiplication in my head, that's 8 times 2 is 6. Carry 1 over. 8 1 is 8 plus 1, 9. Okay, so 9.6. And these 2 numbers, they multiply each other. We're going to have 10 to the power of 8 plus 5 is 13. This one we don't have to change because the decimal is in the right place, okay? So there we go. We have those 2 that you did. Hopefully that wasn't too bad. Okay, now for E. Okay, so notice this line here is all division, okay? Now, when you divide, it's like this. I have 10 times 10 times 10. And then on the bottom, I have whatever I need to divide. So that's 10, 5 of them, okay? And then you know that whenever we have division, things tend to cancel out. This one cancels, this one cancels, this one cancels. I have 2 more 10s on the bottom. So that's essentially 10 times 10 on the bottom, that's 100. And we know 100 is just 10 to the power of negative 2. Oh, hey. Isn't that just 3 minus 5? If I take 3 minus 5, that gives me negative 2. You are correct. Just like adding for multiplication, for division, in terms of exponent laws, you subtract the exponents given you have a common base. So, in other words, that is 10 to the minus 2 for this one, okay? So I give you a chance to try F and G, and we come back and do H together, okay? Good luck. Okay, so for, let's do F. Now I'm going to do the same thing I did with the top. When you're dividing, be very careful though. This is dividing this whole thing in brackets, so that's just 1 times 10 to the power of negative 5. I really don't care about the point 0. That's sig figs. We deal with that later. Essentially, I can do the same thing. I can choose what I like to divide top and bottom, just like for multiplication. I didn't have to care about the order. This seems more feasible, easier to do. 2.3 divided by 1, that is just 2.3, okay? And 10 to the negative 3 divided by negative 5 is just negative 3 minus negative 5 for the exponents, means that that's negative 3 plus 5, giving us a positive 2. So that's 10 to the power of positive 2, okay? All right. Nothing needs to be changed, decimal in the right place. Okay, next one. 10 to the power negative 3 divided by 10 to the power of 5. Okay, so I get here negative 3 minus 5 for the exponents. I'm left with 10 to the power of negative 8. Now we got down to the last one. Woohoo! Almost finished this lesson, yo. Okay, so now we have brackets and we have an exponent outside of the bracket. Okay, so if you remember your exponent laws, this multiplies everything that is inside, every single coefficient, every single unit inside the bracket. So I'm going to have to do 3 to the power of 2 times 10 to the power 8, and that times 2. Okay? So I get 3 to the power 2, 3 times 3 is 9. And then 10 to the power of 8 times 2 is just 16, okay? All right, so this is some scientific notation for you. Please do your practices. Good luck with your examples. I wish you the best of luck. Thank you for watching this video. Fat Mama Physics signing out.